Good afternoon, friends. Myself, Mr. Hungarikar SR. I am presenting a basics of this pharmacokinetics. I am assistant professor from Shivlingeshwar College of Pharmacy, Almala. In last class, we discussed about the order of reaction and pharmacokinetic models. So today we will discuss the remaining parts of this compartment modeling. Compartment modeling is main part where we have to studies here one compartment, two compartment and multi-compartment modeling. There are the different applications of compartment modelings or models where we have to apply these pharmacokinetic models and what is the use of this. If you studies here the pharmacokinetic models is nothing but there are the different pharmacokinetic models: absorption, distribution, metabolism and excretion. These pharmacokinetic models we studies in our body part by using a specific compartments. For that, these pharmacokinetic models are helpful to understand the behavior of drugs in a patient. With the help of these models, you can easily understand or you can easily study what is the behavior of drug in case of the patients. It also helps for the predicting the drug concentration in a various body fluids. In our body parts, there are the different body fluids are there. If you studies in case of the stomach fluids are there. If you studies in case of the intestinal fluids are there. If you studies in case of the spinal cord, spinal fluids are there. So to such different fluids can be easily predicted by using these pharmacokinetic models. This is the second application. Third one, it helps in optimizing the dosage regimen for individual patients. It helps in evaluating the risk of toxicity. It helps in correlating the plasma drug concentration with pharmacological response. It helps in determining the influence of altered physiology on drug ADME. It also explains the different drug interactions which occurs inside the body parts. Next one, after this compartmental analysis, after this compartmental modeling, the next one is the non-compartmental analysis, or it is also called as the model independent method. This is the second method for the pharmacokinetic analysis of a drug. First method is compartmental analysis, second method is the non-compartmental analysis. It follows the linear kinetics. Linear kinetics is nothing but this is the kinetics where the steady state concentration is occurs in case of the body parts, that is called as the linear kinetics. It can be applies to compartment modeling also. In case of this non-compartmental analysis, it will be based upon the different experimental data as well as the graphical data. If you administer the dose, if you administer a dose, single dose to that patient, at that time you have to study what is the drug release. How you can study? You can study by using this mean residence time of a drug, and this is the formula of this mean residence time is equal to area under mean curve divided by the area under curve. Based upon this graph, based upon this formula, you can easily calculate how much is the mean residence time from a for a plasma drug concentration. And if you discuss here the area under mean curve, it is obtained by using a graph. From this graph you can easily calculate. If you plot a graph of plasma drug concentration versus time, it will be shows the mean residence time. Next one, area under curve. This area under curve will also calculate by plotting a graph of plasma drug concentration versus time. This is the graph where if you plot time versus concentration, and by using these points, if you calculate C1, C2, C3, C4, just like the T1, T2, T3, T4, by using the trapezoidal rule. If you use here trapezoidal rule, then you can calculate the area under curve and area under the mean curve. How to calculate this area under curve? They had given in this graph formula. Area under curve AUC is equal to T2 minus T1 into C1 plus C2 divided by 2. And last one, the application of compartment models. This will be used to estimate the thermokinetic parameters like viability, clearance and apparent volume of distribution. It is used in determining half-life, rate of drug release, first order absorption rate and absorption rate constant. Lastly, I would like to thanks for watching this a wonderful slides. Thank you very much.